The title is lying a little bit because I realized that I don't have the time to talk about general isotopies, but instead I will focus on those isotopies which displace the loose Legendrian. And what I want to explain today is how to obtain bounds on the displacement energy of loose Legendrian submanifolds. Okay, but before that, let me introduce some definitions and some notation. So a contact manifold is a manifold which has a hyperplane distribution, and this hyperplane distribution, I will assume that it's always the kernel of some one form, and it's a contact distribution if the n-fold wedge product of the alpha with alpha defines a volume form. And on such a contact manifold, we have a special vector field, the Reb vector field, which is defined by the condition that if you plug it into the alpha, you get 0, and it's normalized by the condition that alpha acting on it gives you 1. So we are interested in, especially interested in so-called Legendrian submanifolds, which are those submanifolds which are of maximum dimension, so dimension n, and which are tangent to the contact distribution, which is the kernel of alpha. So in other words, alpha should vanish when restricted to this submanifold. Okay, so we have this Reb vector field, and the Reb chord is simply a flow line of this Reb vector field, which ends and starts on L. And well, let's say it is parameterized from time 0 to time a, and then a is called the action of the Reb chord. So the standard example of contact distribution of contact manifolds, and actually a local model for all contact manifolds, is the R2n plus 1. And here I've drawn a picture of R3. And the contact form is given by dz minus y dx. You see that the contact distribution does not depend on x and z, but only on y. And if you go in the y direction, it somehow rotates. So these planes here should indicate the contact planes. And d alpha is dx wedge dy. And so the Reb vector field is just given by the unit vector field in the z direction. Okay, and here I've drawn a particular Legendrian, which, let's say, you start on the top, then you go to the front, you go down, and then in the back you go up. And this is everywhere tangent to these contact planes. And it has a unique Reb chord here in the middle, this red line. And the action of this Reb chord is simply given by the length of this line. Okay, so this is the picture in R3. Okay, so we are interested in those isotopies which preserve the contact structure, and those are called contact isotopies. And so an important property of this contact isotopies is that we can associate a Hamiltonian. So we take the time derivative of this isotopy and act with alpha. So this time derivative gives a vector field, and we can act with the one form on it, and this gives a function. Okay, and conversely, if we have a function, so some time-dependent function, which is defined on some interval, then we can associate the contact isotopy by some formulas, and the precise which starts at identity, and these formulas somehow give the derivative, but the precise structure of these formulas will not be important. And what is important is that it follows that there's a one-to-one correspondence between contact isotopies starting at the identity and functions. And by using this one-to-one correspondence between those isotopies and functions, we can define the energy of an isotopy as the energy of the associated function. So if you have an isotopy, let's say, defined on an interval from 0 to 1, then we can define its function as the maximum norm, or as the integral over the maximum norm of the function. So it's the integral over the maximum of this function over the manifold. Okay, and what we want to analyze is how this notion of energy behaves with respect to Legendrian submanifolds. So more specifically, we will today consider, or in this talk, I will consider this displacement energy, which is essentially the minimal amount of energy that is required in order to displace a Legendrian via a contact isotopy. And in this contact setting, displacement always means that there are no reports between the original Legendrian and the displaced version. And so, yeah, so it's the, or maybe more precisely, it's the infernal energy that is required in order to somehow remove all of the reports. And so in general, it is expected that for many contact manifolds, all closed Legendrians should have a displacement energy which is larger than 0. And in some cases, this is actually known. So Dimitroglu, Ritzel, and Sullivan proved that for certain special kind of contact manifolds, namely the quantitization of exact geometrically bounded symplectic manifold, if you have such a contact manifold, then if you have any closed Legendrian submanifold, the displacement energy of this Legendrian is actually bounded away from 0. And they gave an explicit bound, namely it's half the minimal action of the records of L. And well, by compactness of L, this is a non-zero number. Okay, and what I want to explain today is the converse statement. So they here proved that the displacement energy is always larger than the half the minimal action of records, and I will explain how to actually attain an upper bound. And okay, so if you have a Legendrian inside a contact manifold, and I need the assumption that the dimension of the Legendrian is at least 2. So then if this Legendrian is displaceable, then the following is true. So if it has a loose chart, which is contained in a standard ball of height to epsilon, then the displacement energy of L is smaller than epsilon. So there are 2 things in this statement which I should explain. First, what is a standard ball of height to epsilon, and then what is a loose chart. So a standard ball, a ball of height to epsilon is a ball or a ball-shaped set, which in local coordinates looks like this. So it is, here I've drawn the picture in R3, so it's a ball-shaped set, which literally has height to epsilon, or height which is smaller than to epsilon. Okay, so yeah, and the next thing that I need to explain is what is a loose chart. So a loose chart was introduced by Murphy, and it looks like this picture. So you have inside a cube, you have here this knot, and it goes around like this. And okay, if you project it here onto the XY plane, it looks like this. Okay, and you take this picture here times the n-1 dimensional ball of radius radius rho inside the 2 n-1 dimensional ball of radius rho, which should sit in Rn-1 and Cn-1. So this gives an n-dimensional Legendrian inside the 2n plus 1 dimensional contact manifold. And if your Legendrian looks locally like this, then you call this a loose Legendrian. And this picture here is a loose chart. Okay, so the reason why people care about loose Legendrians is the fact that Murphy proved an H principle for loose Legendrians. So what Murphy proved is that, again, under this assumption that the dimension of the Legendrian is at least 2, then if you have 2 loose Legendrian submanifolds which are formally isotopic, then they are Legendrian isotopic. And I will not explain what the precise definition of formally isotopic is, but if you have not seen this before, you can think about it with the following picture. So these large loops here should be the loose charts, And now assume you have these two Legendrians with the two loose charts, and one of those Legendrian has like these two loops here, which somehow go in the opposite direction. So those are opposite loops. And then what Murphy's H principle says is that you can kind of cancel this. So these two pictures are isotopic to each other. And I'm lying slightly here because there was this assumption that the dimension is at least 2, and I'm only drawing the one-dimensional picture, but you should just keep in mind that there are like some additional dimensions which I'm not drawing. And if you want to be precise, you could, for example, take this picture times S1. But yeah, so from now on, I will only draw this one-dimensional Legendrians, but you should keep in mind that they're always hidden dimensions. Okay, so Murphy's H principle says that you can kind of cancel these opposite loops here. Okay, so coming back to the statement of the result. So so the statement was that if L has a loose charge inside the standard ball of vector epsilon, then its displacement energy is smaller than epsilon. And the picture looks like this. So you have this Legendrian L, which has a loose charge, which is contained in this ball of height to epsilon. And then the claim is there exists a contact isotopy, which has energy which is smaller than epsilon, and which displaces L, so which moves L somewhere else so that its image is displaced from L. And the rest of the time I will spend trying to explain why this is actually true. Okay, so now let's first assume that we have such a Legendrian which has a loose charge inside this ball of height to epsilon. So what we want to do first is we want to perturb this Legendrian a little bit to obtain this L tilde here. And this L tilde should be non-Legendrian. And let's say we make this perturbation C1 small. Okay. Now we assumed, of course, that L is displaceable, because if we want to obtain a bound on the displacement energy, then we have to assume that we can actually displace L. And because we can displace L, it follows that we can also displace a small neighborhood of L. But this means that if L tilde is contained and is sufficiently close to L, then we can also displace L tilde from L. So in other words, we can find a contact isotopy which displaces L tilde from L. Now, L tilde is non-Legendrian, and okay, so in the end, we want to obtain a bound on the energy, so we need to somehow obtain a bound on the energy of this isotopy phi. And for this, we can use that L tilde is non-Legendrian. Namely, it was proven by Rosen and Zhang that if we take any connected non-Legendrian inside a contact manifold and we take any contact isotopy, then we can find another contact isotopy whose energy is arbitrarily small and which has and whose image so that the image of L under the time 1 map is the same for both isotopies. So maybe in other words, if you take two non-Legendrian submanifolds, which can be moved onto each other via contact isotopy, then we can actually choose this contact isotopy to have arbitrarily small energy. And this is something that I cannot explain, but maybe it's not too surprising to you that once you make the Legendrian non-Legendrian, you kind of lose all rigidity in this sense. Okay, and so we can apply this here because we have this isotopy phi and this acting on this L tilde. And so what we can conclude from this theorem is that for any positive number eta, we can find a contact isotopy which has energy smaller than eta and which so that L tilde has the same image on the time 1 map for both isotopies, and especially this phi 1 of L tilde is displaced from L. So now we have displaced L tilde from L by using only an eta amount of energy. Okay, so the next step in the proof, okay, this is now the zoomed in picture of the place where we have perturbed L. And the next step in the proof is to approximate a tilde by a Legendrian. So, and to be more precise, you want to approximate a tilde by a loose Legendrian, which is formally isotopic to L. So it's a general fact that this is always possible. So yeah, I've drawn here again these like opposite loops to indicate that L hat here is formally isotopic to L. And now let's go back. So so we have this loose Legendrian, which should be close to L tilde, and which is formally isotopic to L. So this L hat will be mapped via phi to some phi1 of L hat. And if L hat is sufficiently close to L tilde, then phi1 of L hat will of course be also close to phi1 of L tilde. And because phi1 of L tilde is displaced from L, it follows that that we may assume that also phi1 of L hat is displaced from L. So what do we have now? We have this loose Legendrian here L hat, which is displaced from L via an isotopy, which is energy smaller than eta for some positive number eta. Okay, so now remember that we chose L hat in such a way that it is formally isotopic to L. And what this means by Murphy's H principle is that we can actually find an isotopy from L to L hat. So yeah, so we can find this isotopy which maps L to L hat, and actually because the perturbation of from L to L tilde and then the approximation L hat can all be assumed to have some more support in this ball, and also the loose chart is contained in this ball. We can actually assume that this isotopy psi has support contained inside this this ball here. Okay, so now what we have is we have this isotopy psi which moves L onto L hat, and then we have this isotopy phi which displaces L hat. So if we concatenate these two isotopies, we actually have an isotopy which displaces L, and this is what we want in the end. But the problem is that so far we have no bound on the energy of this isotopy psi. So so in order to finish the proof, we need to find a way to bound the energy of this psi. And for this, we can use this the structure of this set of this ball of height to epsilon. Okay, so okay, so now let's just assume we have such a ball of height to epsilon, and inside of this ball we have so we have an isotopy which has support inside of this ball. What we can do with this ball is we can squeeze it. So we can squeeze this ball of height to epsilon to obtain some kind of very thin ellipsoid. Let's denote its height by lambda. So this is an ellipsoid and its height is smaller than lambda. And corresponding to this isotopy psi, we have an isotopy psi prime, which has support inside this ellipsoid U lambda. And now there are two important facts about this squeezing procedure. So the first thing is that actually it takes only an epsilon amount of energy to squeeze this ball of height to epsilon into arbitrarily small ellipsoids. So this can be proven by just writing down explicitly what this contactomorphism looks like that squeezes this ball. And you will see that in the limits that you get, let this lambda go to 0, the energy will converge to epsilon if you choose appropriate contact isotopies. And the second important point is that actually the energy of this isotopy psi prime will go to 0 as you let lambda go to 0. So, and again, this follows essentially by writing down explicitly what the squeezing isotopy looks like. Okay, and with these two effects, we can now finish the proof. Namely, what we can now do is we can squeeze this ball, which we have here, and the squeezing takes an epsilon amount of energy. And after we have squeezed it, we can perform this psi or maybe psi prime then, and which now has an arbitrarily small energy. And after we have performed this psi or psi prime, we can perform this isotopy phi, which moves, which displaces the Legendrian, and this has also arbitrarily small energy. And in total, so let's say this psi also has energy smaller than eta. So in total, we have, if we concatenate all those three things, the squeezing, the psi, and the phi, we get epsilon plus 2 eta energy. And because eta was arbitrary, we can conclude that we can displace L by using some epsilon amount of energy, or maybe epsilon plus a little bit, which can be arbitrarily small, and we conclude that the displacement energy of L is bounded by epsilon. So yeah. So maybe again to summarize the proof, we first perturb L into a non-Legendrian L tilde because we know that we can kind of move from an energy perspective, we can move non-Legendrians freely through our contact manifold. And so we can displace L tilde from L, and then we approximate L tilde by a loose Legendrian and use Murphy's H principle to construct an isotopy from L to this L hat. And then we can use the structure of this ball of height to epsilon in order to get the energy bound on this side. And okay, I think these were all slides that I prepared, but maybe since we started a bit later, I have like a few more minutes to say something. So I thought I wouldn't finish in time, so that's why I not prepared any more slides. But so let me just say something about possible generalizations of this. So here we only considered isotopies which displace L, but you can do more general things. Namely, assume you have now two Legendrians. So let's say L1 and L2, and you have an isotopy between those. And now you have both of these Legendrians have some loose charge, which is contained in a ball of height, let's say epsilon or 2 epsilon 1 and 2 epsilon 2. And by doing the exactly same constructions to both of these Legendrians, so on both sides you can squeeze the balls, and then you have you can perturb the Legendrian to non-Legendrians. You can connect the two non-Legendrians by something which is arbitrarily small energy, and then you approximate the non-Legendrians by loose Legendrians and apply Murphy's H principle to find to connect everything up by a contact isotopies which are supported in these two balls of height to epsilon. And by doing the exact same thing just on both sides, we can actually conclude that we can find an isotopy between the two Legendrians, which has energy like of order epsilon 1 plus, which has energy epsilon 1 plus epsilon 2 plus some eta, where eta can be chosen arbitrarily small. So you can actually do this for arbitrary isotopies between two loose Legendrians, which have such loose charts and balls of some height. And maybe let me just mention that you can actually do this whole procedure somehow C0 closely. So okay, of course, you don't get a C0 bound on this psi, but you can, in a certain sense, get a C0 bound on this phi. So if you have an isotopy of this L and move it somewhere, then first you perform this psi, which gives you this L hat, and this L hat can be assumed to be C0 close to L. And if you restrict some of this phi to L hat, then this will be C0 close to the isotope, to the original isotopy that you had acting on this L. And this can you show that you can actually achieve this C0 closeness. And yeah, and maybe one last remark. So in the abstract, I mentioned that this somehow can be interpreted as a quantitative version of Murphy's H principle. And this goes in the following way. So assume you have two loose Legendrians, which have such loose charts and these balls of some height. And you assume that those are formally isotopic. Then by Murphy's H principle, you know that they are actually genuinely isotopic. And by what I've explained so far, you can actually obtain energy bound. So from this, you see that you get actually Murphy's H principle, but additionally, you get a bound on the energy of the isotopies that whose existence is implied by Murphy's H principle. And yeah, okay. And I guess this is now all I want to say. So thank you for your attention. And so yeah, so feel free to ask questions.
Thank you.